Good. So, good afternoon. Uh, so, what we saw in the last class was, yeah, I said the process of making glass is rather simple. You start with SiO2 is the base material. There are also other ingredients added to it, but this is a source material, and you take it to its melting point, melt it, and when you rapidly cool it, room temperature, you get the glassy formation. So the generic name is glassy formation because this process of cooling the melt rapidly to the room temperature doesn't allow the atoms to settle down to their lattice positions. And then I also mentioned that the same melting process is required to make single crystals. Yeah, but I said the single crystal process is rather tedious, so rather tedious process. It's also very expensive, especially if you want to grow larger crystals. So you get silicon as a raw material in polycrystalline form. You melt it in what is called the CZ method, Tchaikovsky method, and there's a slow cooling process involved. So here in this case, there are two ways of doing it. Either you move the hot zone away from the mold, from the melt in a slow way, but the easiest thing is to pull the crystal out of the hot zone, so it goes through a delta T variation within 3 to 4 heat zones. You know, that's why you have a slow cooling process leading to crystallization and formation of a single crystal. And I also mentioned that for a polycrystalline material, to form a polycrystalline material, per se, we do not need a melt. So polycrystalline material can be obtained from powders of the raw materials. If you just heat a powders, the mixture of these powders as a thumb rule to about 90 to 92% of the melting point of the constituent elements. Right? That's enough. You don't have to actually start from melts to get a polycrystalline material. But for single crystals have to be grown from melts. And on the other hand, rapid cooling of this leads to the material forming in the form of its glassy form. So any material can form in its glassy form, which is a non-crystalline form. Okay. Just to continue in that line, to say that silicon dioxide, I said you get silicon and you go all the way to making solar cells. You form glass there, and the same silicon dioxide, if you get it in a crystalline form, quartz can also be obtained in a natural crystalline form. I showed this to you. This is quartz, right? You see, so the crystalline form of silicon dioxide is called quartz. And the non-crystalline amorphous form of silicon dioxide is glass. Both have great advantages, great applications. You need plenty of glass in the day-to-day applications. And quartz is, of course, it has this fantastic application of quartz being used in quartz windows as quartz crystal for, in piezoelectric devices. And today, you can't think of a watch without a quartz crystal. It's basically quartz runs the watch movement, whether it is a wristwatch or a wall clock. Everything is to do with quartz crystal here. You see the diverse applications that you can get the moment you get silicon dioxide in a crystalline form and a non-crystalline form. I think this is a very beautiful example of silicon dioxide. And again, from SiO2, you get silicon as a raw material for making, crystals. And you can also dope these silicon crystals into a p-type silicon and an n-type silicon by boron, phosphorus, nitrogen doping, and of course all that goes into making your solar panel, right? The photovoltaic stack. Look, these photovoltaic stacks, silicon-based photovoltaic stacks, can also be made with polysilicon, where you have the silicon itself is in a polycrystalline form. That means over a given area you have grains and grain boundaries. You can also get a photovoltaic panel using completely single crystalline silicon. So the difference in both the cases will be, one will be inexpensive, the silicon panel made out of polycrystalline silicon. The single crystalline silicon wafers or photovoltaic panels are very expensive, but what you get with polysilicon is about 13 to 15% of efficiency of conversion of the solar radiation. Whereas if you get a silicon panel using single crystalline silicon, the efficiencies can be pushed up to 26%. So it depends again on applications. What kind of applications are you looking at? For example, in villages in Gujarat, Rajasthan, the desert area, where they can't afford to have electric poles. This has been one of the problems because of the gusty winds and all that. So what has been found was the easiest solution is install a polysilicon based photovoltaics on rooftops of houses. This has solved the problem in a very big way. But then when you, so yeah, this is a typical application of a rooftop photovoltaic cell. And of course, the satellites and space labs, they're all powered by silicon, always. Also gallium arsenide based photovoltaics. So the silicon that goes into, powering the satellites and the space labs is made of single crystalline silicon, because you want the highest efficiency there, and also you want these panels to last for longer periods, right? As long as sometimes the life of the satellite is determined by the panel life. It's as simple as that. But then once you have these panels in a single crystalline form with efficiencies of 26% or so, these panels are supposed to work for 20%. Of course, there is always a degradation of the quantum efficiency as a function of time as years pass by. But what happens is, one of the problems these outer space labs and satellites face is, depending on where they are placed above the Earth, all the way from 400 to 1,000 and so on kilometers from the surface of the Earth, they are exposed to continuous bombardment of extraterrestrial radiation. Especially they get exposed to X-rays and gamma rays. And any material that is continuously exposed to radiation, if I take quartz crystal, and if I put it in a gamma ray reactor, what happens is the high energy radiation causes defects in solids. And these defects can start deteriorating the performance of these solar cells. So this is, again, one of the major issues of using solar panels in satellites. But there are solutions worked out, there are solutions for everything. But this slide so beautifully summarizes the examples pertaining to SiO2, all the way from beach sand, how you get glasses, the importance of quartz in many devices, including watches, and you get silicon out of silicon dioxide, and go all the way in making high quality, solar panels. So today there's also, of course, a lot of research going on as to look for alternatives of silicon in manufacturing, fabricating photovoltaics. It's required, that's how research works. You can't say that it's only silicon that can be used as a solar photovoltaic forever. So there are alternative materials. There are now perovskite based solar cells are being researched in a big way. Dye sensitive solar cells, the various alternatives that are being worked out. Okay. So the crystal that we grow, finally, it's about how you determine whether this large bowl of silicon is crystalline or not. Ideally, this is the way the unit cells have to form inside a crystal. That means this unit cell and this unit cell are correlated in the sense that there are no misorientations. There's a perfect periodic way of arrangement of atoms in the crystal, all the way from one end to all the 3 dimensions. That means this entire volume should have atomic arrangement in this way, in the perfect periodic way, in all 3 dimensions. But there are no perfect crystals, you know that, right? Crystals always have defects because, the process of crystallization happens when you start cooling the material from its melt. That means the process of crystallization starts from very high temperature, which means at those temperatures, there is a lot of possibility of atoms escaping from the matrix. Okay, so which means one of the most common defects that you find in crystals is point defects. Point defects are missing atoms. Point defects are inherent to any crystal. Even if you get pristine diamond crystal from Earth's crust, it will have defects in it. Okay? And radiation damage can also create crystal defects. We'll see some of this today. Yeah. So this is the ideal situation. All the unit cells are perfectly arranged in all 3 dimensions. Even in the so-called good crystals, there's no perfect crystals. Good crystals, you'll still have missing atoms. We will not have grain boundaries. We will not have dislocations, but missing atoms are always a part of any crystal. Okay. Yeah. So a polycrystalline material, easy to make. A single crystal takes a lot of effort. Okay. And a polycrystalline material typically looks like that. It has grains and grain boundaries. Grain boundaries are defects where you don't have the regular atomic arrangement. The atomic arrangement of atoms terminates there. You'll have loosely bound atoms in the grain boundaries. It's nicely shown here. And of course, these blocks are the basic building blocks, these unit cells. So you can see that when you reach the boundary, you'll have the unit cell arrangement terminating, and then it continues in the next grain. And the relative orientations of the unit cells in this grain and the neighboring grain could also be different. Okay. Suppose this unit cell gives rise to let's say an electric dipole in a particular direction. This electric dipole in one unit cell could be this one in one unit cell could be okay. So if I'm looking at the granular structure, so when it comes to a specific looking at so if the effective electric polarization in this single crystalline grain is in that direction, the neighboring grain could be in that direction, that direction, that direction, that direction. See, this is possible. But then if you have if all these dipoles are in one direction, you have a large electric dipole or a large magnetic dipole. So that can also be achieved using an applied electric field in the case of a ferroelectric, applied magnetic field in the case of a magnetic material. But basically, in that case, these electric dipoles have to surmount the barrier energy to align themselves in the direction of the field. Well, so yeah. So this is the ideal situation that I would like to have, a crystal, perfect crystal, where you see these alternating green and blue balls. This is an ideal situation, but there are no ideal crystals or real crystals. So at the most you get a highly crystalline lattice with certainly missing atoms. So that's a polycrystalline material. You can also get a given material in this form. This you call it the microstructured or nanostructured growth, where each of those small domains or balls is equivalent to a crystalline region, except that the scale is different. Here, if you look at the scale, this is a 1 micron by 1 micron scale, and this is a 50 micron scale. So in a 15 micron scale here, what you see is grain sizes ranging from 5 to 50 almost. And here on a 1 micron scale, you see how many number of these small regions you see, right? So this is a perfect example of the formation of the quantum dots. If you go down to this level between 0.25 and 0.5 microns, and you look at that block there, and you can count how many are there, and we can estimate the size to be anywhere from 50 to 70 nanometers. So this also in one way is a polycrystalline way in which the material forms, which is different from this just in the sense that the size scales are different. So these are called the nano dots. The nano dots formation is what exactly you see here. Okay. Now, yeah, it's very interesting. Yeah. But so if I go to one of those dots, one of those quantum dots, again in one dot of say 60 nanometer cube, if it is perfectly spherical in shape. So inside the 60 nanometer cube, you'll have all these unit cells arranged in a regular periodic way like that, right? So the scales are different. And what you see on the bottom of the right-hand side is what happens when this polycrystalline material is transformed into a thin film using the thin film growth methods. You'll see normally thin films will give you a smooth surface morphology. That itself is basically an indication that, but again, the scales are, here the scale is only 2 micron by 2 micron square. So it's a 2 micron square area. But on this area, if you look at, I mean, you can also extend the scan to 10 micron squares, 100 micron square, like this one. And if you don't see the formation of these kind of grains and grain boundaries, then you know that, yes, the thin film could be, and also if it gives a very smooth, microstructure, the surface roughness is just a few angstroms, you know that you have a single crystalline growth. But again, we can't conclude many things. Even if it is obtained, if the thin film is obtained in an amorphous form, non-crystalline form, still you get a good surface smoothness. Still you may not see grain boundaries. But then to determine that it's actually a crystalline thin film. That means you transform this polycrystalline material into a crystalline thin film. You need to do diffraction. Also, one more interesting thing is when you get a material obtained in a thin film form, there are two things. One is you can confirm by looking at the microstructure that there are no grains and grain boundaries, which is a good sign. Second, when the surface roughness is very small, then this is what is required for device applications, especially when you're going for multi-layer growth. You know, if I want to make a GMR device or a tunnel junction, I have two electrodes, which I deposit in the form of two layers, each layer having a thickness of 30 to 50 nanometers. And then you have an intermediate layer, which has a much smaller thickness. So imagine if when I'm growing one layer after the other, the surface roughness of the bottom layer should be extremely smooth. So this is where the technique plays an important role. It's very important. The substrate plays an important role. All the parameters play an important role. So there are some systems where you know that theoretically, if I build a tri-layer system, I would see this property, but then you may not have a method to achieve the tri-layer, because to get the tri-layer, the bottom layer has to be deposited on a certain substrate, and there could be a lattice match between the substrate and the first layer. And once there is a lattice match, you know, the surface morphology gets affected. These are all interlinked, right? Lattice mismatch, and also your thermal expansion coefficient. All these things come into play. So for multi-layer growth, you need an extremely smooth film. Well, you know, today we have methods by which you can grow thin films with surface roughnesses of the order of 3 to 4 to 5 angstroms. That means at the atomic level corrugations only. So any surface is said to be optically flat. If you want to declare a surface to be optically flat, it has to have a surface smoothness of the order of just a few angstroms. This is where it becomes so important when all these powerful lenses are made. You know, lenses have lenses that go into all these gadgetry cameras, especially the lens that is used in Hubble telescope. We talk about aberrations in lenses. The aberrations toward the edges in lenses is because of the subtle variations in the surface roughness. Subtle variations can create a large amount of distortion in the image. This was initially the problem when Hubble went into the outer space more than 20 years back. It started sending distorted images. Then the NASA scientists found that it's a problem with one of the lenses, the way it was polished. The surface finish was not to the specified value. Then that was corrected. You know, a new lens was sent. The existing one was replaced, and now you see the kind of images Hubble sends of the extraterrestrial object. This is just amazing. I mean, the kind of information that you get from this telescope is just amazing. But you know, a lot went into making those you know, highly polished lenses. Even for the discovery of gravitational waves, you know, the quality of the lenses used, because the laser beam is shot into two directions, and you know, the surface quality of the lens has to be extremely precise. Okay. So the surface smoothness plays a very crucial role, you know, during thin film growth process, physical property measurements, and applications. But well, I keep talking about the fact that grain boundaries of this nature, what you see on the screen, you don't want them, because obviously now I think more or less you could guess what happens if I get a material. Go back to the example of silicon. If I get silicon in a single crystalline form, in this form, and the same silicon in a polycrystalline form, what do you expect? You know, so you don't expect changes in the crystal structure, because this building block is very small, few angstroms in length, if you're looking at a unit cell of silicon or any other material. But so you also see all those unit cells arranged in a perfect periodic way. The problem is the grain boundaries. So this effect will have a bearing on the physical property. So if the same silicon is obtained in this form and that form, now imagine if I'm measuring, if I want to do electrical property measurement on the same material, silicon, which is in polycrystalline form and a single crystalline form, when you start passing a current, I told you in the last class that current always prefers to flow through the least resistive path. So grain boundaries are high resistance zones. So this can be looked at as a series of low and high resistors connected. Whereas here the current flow will be much smoother. And you can imagine the regular rho versus T that you see for a semiconductor. The value of resistivity will be more in this case compared to a single crystalline thin film. Okay. So, but grain boundaries are not all that bad if you start controlling them. Today, we talk about the physics of defects, physics of controlled defects, physics of controlled grain boundaries. This is just amazing. The other part of this story, you make a polycrystalline material, the material forms into this granular structure. But then imagine if I have, this is one side of the grain, two crystalline regions separated by this grain boundary. Today we are in a position to control these grain boundaries, right, in such a way that we can make devices. So the whole GMR, giant magnetoresistance, especially the TMR devices, tunnel magnetoresistance, all these devices go into our computer hard drives. The computer hard drive technology is all driven by the GMR technology, for which Albert Fert and Peter Grunberg got the Nobel Prize in 2007. It's a complete revolution, the way information storage is happening with the GMR read and write heads. But today, the GMR technology is all based on controlling the layer thicknesses, especially the TMR part, the tunnel magnetoresistance, where the process of tunneling is involved from one side of the electrode to the other side of the electrode. And I'll brief about the process of tunneling, how it started. It's now almost 7 decades of research from the days of Josephson tunneling. And today we have Josephson devices that can be fabricated in thin film form with precise control of grain boundaries. And Josephson switches are made. And even after 4 decades, it is still the Josephson switches that are used in supercomputers for time sharing of the central processing unit. Just amazing. So all these tunnel-based devices, to do the physics of tunneling, we can actually now today deposit, imagine a part of this granular structure. That's what I'm showing here. So I have one layer here, another layer here separated by a thin boundary. So I can control these boundaries. So I can tune the physical properties in the way that I get useful device applications. But the physics of the process of charge transport through these barriers itself is a vast field. Okay, so this is what I'm telling. If you want to have this as a bottom layer, and this as another layer on top, and in between you get a thin layer, you need to optimize the growth processes in such a way that each layer should have an extremely smooth surface finish. And it should be almost optically flat. And that's what I try to show here. Okay, So going back to this first polycrystalline material. So what you can understand, what you've understood probably by now is you have a polycrystalline material in a bulk form like this. A polycrystalline material has these defects, and you can transform this polycrystalline material into a single crystal, and you can also have material in a powder form from which thin films can be grown. But then I want to just go one step ahead and explain how these polycrystalline systems are formed. For that, you need to have a certain idea about diffusion. It's all about diffusion. Let's say you have a simple material by this formula, MgAl2O4, magnesium aluminum oxide. It has what is called a spindle structure. Let's say I want to form magnesium aluminum oxide. I can start with magnesium metal, aluminum metal, and then you subject these metals to react with each other in the oxygen ambient, and then you expect this new phase to form. I also said that when you're looking for new phases to form, you first have to look at the thermodynamic feasibility of the formation of the new phase. Right? There are phase rules. There's what is called the Gibbs phase law, and then first we need to find out from the phase diagrams. There are several volumes of phase diagrams from which you can easily find out whether first a reaction between these two compounds is possible to get a new one. Right? Sometimes the phase diagram says if you want to take alumina, Al2O3, and you want to dope alumina with a certain element, the phase diagram may not allow that to happen, which means you cannot dope alumina with a certain element because of the changes in the respective enthalpies of those two systems. Okay, so let's say that a reaction between these cations is feasible, but normally we don't start with the metallic parts of a ceramic like this. MgAl2O4 is a perfect example of a ceramic. So what I'm going to tell you is how a ceramic is made. Suppose you want to make a target of MgAl2O4, which you want to use in a sputter deposition, right? So the target that you make itself forms in polycrystalline form, but that itself has, there's a lot of procedure involved before you start using it in a thin film. So how the target is formed is what you're going to see. So the basic way to start with MgAl2O4 is you first look for the constituents of magnesium and aluminum. Since this is an oxide compound that you want as an end product, the best way is to look out for the most stable oxides of magnesium and aluminum. So and today you can also in earlier days, if I know that the most stable form of magnesium is magnesium oxide, I have to go and prepare it in the lab by chemical process, and then the obtained compound may have some impurities. Removing trace impurities is always a big challenge. But today there are companies that are there that produce these high pure compounds. You talk about 99.9% purity and 99.999% purity. So between 99.9% purity and 99.999% purity, there's a lot of cost difference. But for most of the lab scale research, 99.9% purity is okay. That means you still have 0.1% of certain impurities. Okay, these are like standard elements like iron, nickel, chromium, etc. So you take magnesium on one side, which is a more stable form of Mg, and the most stable form of aluminum is Al2O3, aluminum oxide. So both have different melting points, both have different structers. So what happens is when you make a reaction to happen between Mg and Al2O3, it's all about interdiffusion of ions from one side to the other, right? So let's say you start with a block of MgO, Al2O3, and for diffusion to happen, diffusion cannot happen at room temperature. So you need a high temperature process. You can see this, the way uh, a product layer forms X square depends on the temperature, okay? 1300 degrees centigrade, 1400 and 1500 degrees centigrade. And the number of hours that it takes to form a product layer is certainly less at lower temperatures compared to the higher temperature. And when I say high temperature, what is the highest temperature you can go to? Or the highest temperature you can go to is also dependent on the melting point, highest melting point of one of these constituents. If the melting, we know that melting point of alumina is very high. So if you go to that melting point, I also told you that for a polycrystalline system, you don't have to go to the, you don't have to melt the material. But then again, if you are going to the 92% of the melting point, still it is close to 1800 degrees centigrade here. And by which temperature MgO might melt off, it depends on, you know, so you go to the lower melting temperature of the one of the constituents. So if one compound has a melting point of 1500, the other one has 1800, you should settle down to heating the compound at 1400 degrees centigrade so that you won't start melting one of them. Now, what happens when you subject a combination of these two to high temperature heating? You'll start, so there can be no diffusion at room temperature, obviously, because you need to give energy to these ions to diffuse across. And so what we are doing in that process is, when you subject this block consisting of two blocks of MgO and Al2O3 with an interface there, right? So only when you go to higher temperatures, the individual bonds of Al2O3 and MgO, where each one has its own crystal structure, they start weakening, and that can allow the interdiffusion of ions can happen, right? So interdiffusion is a perpetual process, even if you leave a compound at room temperature, because room temperature itself has some energy, 26 milli-electron volts, right? A thin surface layer, the atoms on the surface layer can gain that energy, but normally this energy is not sufficient to cause any kind of diffusion. So you need elevated temperatures. So you see that what happens here is magnesium ions start diffusing to the right, aluminum ions start diffusing to the left, and at the interface, the boundary, the new reactant product forms. Okay, magnesium is always in the valence state of magnesium is 2+, the valence state of aluminum is 3+. So for every 2 aluminum ions that diffuse to the left side, you'll have 3 magnesium ions, 2+ ion moving to the right side. So that's for the basically for the charge balance. But the question is the following. So if I have, say, magnesium oxide in this form and aluminum oxide in that form, so I'm physically bringing them together, and the reaction is happening at this interface because the diffusion is across. So the reaction surface is the surface at which point these two blocks are touching with each other. So we have created a nucleation site in the form of a certain area, and the interdiffusion is happening only in that area, and the new product is forming there, certainly, right? That's what you see here, this hatch line. But then, see, if you imagine how long it takes, if I take, if these are the actual sizes of magnesium oxide and aluminum oxide. Let's say these are the actual sizes. You can see it's about a centimeter in diameter and 2 centimeters in length. If I take aluminum oxide and magnesium oxide of this size, and if I want to see a reaction on the product formation at the interface, it will happen. But for the entire magnesium oxide on one side and entire aluminum oxide on the other side to form into a new product, you know, it will take several years, because diffusion in solids is such a slow process, very, very slow process, right? So the perfect example of diffusion through a gaseous medium is the fastest. Even though the process is the same, suppose in my room, someone enters with perfume spray and he sprays it there, and I can smell it on the other end of the room within a split second. So that means the particles, molecules have diffused everywhere in the room within no time. Okay? Now the diffusion in liquids, example is you take a beaker of water, and if you're using an ink pen, put a drop of the blue ink or black ink, you see how nicely the drop spreads into the entire liquid, even without shaking up the beaker. But compared to the first example of a perfume sprayed in a room and a liquid drop diffusing into the liquid, the second process is slower. In a solid, its diffusion is much, much, much slower, because all the atoms are formed into a regular solid lattice. So first of all, you're trying to weaken the bonds between these atoms, right? You're not completely breaking them. The high energy is sufficient to make the atoms sort of loosely bound, right? And then you're making the diffusion to happen. So that's why I said it is so important for diffusion in solids that high temperatures are very important. But let's say a solid has a melting point of only 1000 degrees centigrade. There's no question of going up to these temperatures. So you have to do the heating for a polycrystalline material below 1000 degrees centigrade only. So you can imagine the diffusion rates will become much lower. So just to give you some numbers, diffusion in solids, even at elevated temperatures, happen in time scales of, if I give you the length scales, it will be just a few microns, nanometers to micrometers, even after heating it for an hour or so. It is so slow. One can calculate the diffusion lengths and from the diffusion coefficients. You know, we can estimate the diffusion lengths in solids. So it's an extremely slow process. So the reaction between two solid pieces, even though you see the products at the interface, because that's the only place where you created the nucleation site. This is a nucleation site. So thin film growth, any growth, single crystal growth, it's all about nucleation. Even the big bowl of silicon I showed you, right? The big bowl of silicon I showed you that grows out of this molten silicon using the Czochralski process. The starting point is a silicon seed. The already grown seed is used on which the nucleation happens. Then it grows. So nucleation is very, very important. And nucleation leading to diffusion. And so if we can provide a large number of nucleation sites, obviously the reactivity will be much faster. So that's what, that's a new product, right? This is typically what is called the Kirkendall effect. In fact, today there are furnaces in which one can demonstrate the Kirkendall effect. That means change in color at the interface. It means you can clearly see, oh, at this temperature, I see the formation of a new phase. at a given boundary, which is called the Kirkendall effect. But if you want to increase the reaction rate, this is not the way to go. You can't make two solids to react with each other. That's a very time-consuming process. Yeah, you see that the surface structures of magnesium oxide crystals displaying various facets. No, this family, the 100 family, has that arrangement, and the 111 face of families will have the arrangement like that, and the 111 phase of oxygens arranged like that. You see that, and you have an octahedron, a cubooctahedron, a cube. Depending on which of these phases is more stable, when you are forming two compounds, right? So you're breaking atoms, and the new phase is forming. So when the interdiffusion is happening, these diffusing spaces will start settling down on one of the most stable existing phases, and the phase builds up. It's almost like growing a thin film on a substrate. You know, for everything there's a support that is required. That's why I said you really don't have to break up the entire solid into its molten state. So the polycrystalline formation is faster, I said, because you already have these existing phases, right? So by causing the diffusion to happen, if these ions come, if already the 100 phase of one of the systems is intact, and if the 100 phase is also existent in the final compound, and that becomes a platform for magnesium aluminum oxide to form, because that 100 phase is already present in one of the constituents. So nice to see that, right? So that becomes all the 100 phases become the platforms for nucleation, and the new phase starts building up there, and finally the crystallization process will complete. But the crystallization process happens, and you see the new phase forming there. But then the whole question is about how do I increase the process of reaction so that I get the entire volume of MgO and the entire volume of alumina, especially for the sizes I showed, to get converted into the new phase. You can't start the reaction to happen in the form of these blocks. It's where I break it up into smaller pieces, and I create a large number of nucleation sites. In fact, thin film growth is all about it. You're actually breaking it up into atoms. So you're actually making the individual atoms to react. That's why when I want to convert the polycrystalline form of this one, the polycrystalline form might take, say, several days, because the solid state reaction process takes several days. For me to get magnesium aluminum oxide target, which I use in the sputter growth, if it takes 5 days, I can get a crystalline thin film of magnesium aluminum oxide using a thin film growth process. I get a high degree crystallinity of magnesium aluminum oxide, which I grow from the polycrystalline counterpart of MgAl2O4. The thin film growth process might take not even 30 minutes. I get highly crystalline thin film. We'll see how this happens in the next class. So the next class will be on Wednesday. I think I sent all the links for this week. We'll again meet on Wednesday so that we'll have continuity beyond this point. Okay. All right.